Hi, this is the first lesson in Unit 6, Topic 2. Please make sure you have a packet, that you've picked up a packet. And on the back of the first page, I'd like you to complete the warm-up. So please pause this right now and give yourselves a few minutes to do the warm-up. All right. It wants to find the coefficient of the y to the 6th term in that expansion. So we want the y to the 6th term. So it's going to go from the 10th power to the 9th to the 8th to the 7th to the y to the 6th. So this is going to be, this normally starts at 0 out of 10, 1 out of 10, 2 out of 10, 3 out of 10. So this would be 4 out of 10, or 10 C4. And then with the 6th power, this is going to be 2y to the power of 6, and the second term is -3, so it would be -3 to the power of 4. You're going to take 2 to the 6th power, which is 64. So this is going to be 10c4 times 2 to the 6th power times y to the 6th power times -3 to the power of 4. So 3 to the 3rd is 27, 3 to the 4th is 81, times y to the 6th, times 2 to the 5th is 32, so this should be 64, and then whatever 10c4 is. So pop that in your calculator, and your coefficient of that term is 1,088,640. All right, go ahead and flip into page number 3 in the packet. And it's asking us to define what a sequence is. Define a sequence. So it's a list of ordered values following a specific function rule. So what you don't actually end up seeing in the sequence is the input values. So the first thing they're asking us to do is to write the first 6 values of the following sequence and then graph it. And then the sequence they want us to use is n-1 over n here. So a of 1 is the first. We call a of 1 the first term. We plug a 1 into our equation, 1 minus 1 divided by 1. So this is going to be equal to 0 over 1, which is 0. Second term, it's going to be n is 2. 2 minus 1 over 2, which is 1/2. A of 3. 3 minus 1 over 3, which is 2/3. And then you keep going. A of 4 is going to be 4 minus 1 over 4. A of 5. 5 minus 1 over 5. A of 6, 6 minus 1 over 6. So this is equal to 3/4, 4/5, and 5/6. So what we end up plotting is the term number. So the x-axis is the term number. So this is the first term, the second term, third term, fourth term, fifth term, sixth term. And this is up at 1 here, because our numbers are between 0 and 1. So at the first term we're at 0. At the second term we're at 1/2. Third term is at 2/3. Fourth term is at 3/4. 4/5, and 5/6. So that is what the graph of our sequence looks like. Now, next piece here is to find the first 4 terms and then the 25th term. So the first term is a of 1. So that's going to be equal to 3 times n, 3 times 1, plus -1 to the first power. So this is 3 plus -1, which is 2. A of 2 is our second term. 3 times 2 plus -1 to the second power. You need to make sure you keep those parentheses there. That's going to make this 6 plus positive 1, which is 7. A of 3. 3 times 3 plus negative 1 to the third power is 9 plus negative 1, because negative to the odd power is going to stay negative, is 8. And A of 4 is 3 times 4 plus negative 1 to the power of 4. 12 plus 1 is 13. Now what it's asking for is the 25th term, done exactly the same way. You're trying to find A of 25. So 3 times 25 plus negative 1 to the power of 25. Negative 1 is being taken to an odd exponent. When it's an even exponent, it's positive. Odd exponent is negative. So this is going to be 75 plus negative 1, which is equal to 74. All right, this is one of the harder things we actually do in this section. What they're asking us to do next is to look at this pattern and figure out what the sequence rule is. So as you go from 1/2 to 1/4 to 1/8 to 1/16, what we're really doing here is multiplying each of these times 1/2. Denominator is being multiplied by 2, which is the same as multiplying by 1/2. So I'm really looking at this being like an exponential function, where A is the starting value, B is the growth rate, and like X or N would be your time. We'll make it an X. So again, this is your initial, and this is your rate of growth or decay. So the way we write a function rule is A of N equals our first initial value, which is 1/2. 1/2 to the power of N. So we're starting at 1/2, and we're multiplying by 1/2 each time. So when X is equal to 0, A is going to be equal to 1/2. A is going to be equal to 1, and B is 1/2. That's why this starts with a 1 times 1/2 to the power of N. Next one over. So this is really E to the first over 1, E to the second over 2, E to the third over 3, E to the fourth over 4. So hopefully you can see. Whoa. Sorry, this just went exploding off the field. Okay. That's not working. Is this working yet? Okay. Wow, back in business. That was exciting. Okay, so as you notice, the pattern A of N is equal to E to the power of N over N. Again, here's our first term. This is a 1 over 1. Second term, 2 over 2. 3 over 3. That's why the N's are there. Third one here. This is a 1, 1/3, 1/9, 1/27. So we're multiplying by 1/3. Our first term that we multiplied by 1/3 to get 1, to get our first term here, A of N is equal to 3. Our rate of growth is 1/3 to the power of N. Okay, down below, write an expression for the nth term, so find what A of N is of each sequence. So this kind of goes back to Algebra 1, where you started to look at patterns and notice whether it's a linear, quadratic, cubic, square root, sort of a function. So if I go from 1 to 3 to 5 to 7, I am adding 2 each time. It's a constant rate of change. So that means that is a slope of 2. Slope, which is 2 over 1 or 2. So this would be A of N equals 2N. And our first term, if we back this up to the 0 term, if we subtract 2, is going to be down at -1. So again, we want the 0 term, So when, this is the slope, I was thinking back to in AP Stat we use different letters, but in algebra we use M for slope and B for the y-intercept. And the y-intercept is when the x value is 0, so it's whatever the 0 term is, so that's why we're backing it up a step here. Our next pattern here, we are adding 3, adding 5, adding 7. So as I look at this here, the first difference isn't constant like it was with the linear function here. Our second difference is constant. If you notice, if you look at the second difference between these two, it is constant. That makes this a quadratic function. If your third difference is constant, that makes it a cubic function. So, our first term, if we made this a of n equals n squared, would be 1, right? If we plugged a 1 in here, 1 squared would be 1, but the answer is actually 2. So we took that and we added 1 to it. If we plug a 2 in here, 2 squared is 4, 4 plus 1 gives you the 5. If you put the third term in here, 3 squared is 9, we had to add 1 to get to the 10. When you put your fourth term in, 4 squared is 16, you add 1 to get to your 17. So your pattern is a of n equals n squared plus 1. Okay, the next concept we are looking at here are the limits of the sequence. And this is our last page, I believe, before our homework. Okay, so limits are something you are going to be spending a lot of time with in calculus next year. And if it's not next year, when you eventually take a calculus course. So we want to figure out if the sequence is going to converge or diverge. And when it converges, it ends up approaching a certain number. So this approaches a constant. If it diverges, it's not going to approach a constant number. So as you look at what's happening here, this is going from positive 1 to negative 1, positive 1 to negative 1, positive 1 to negative 1, and it keeps doing that pattern. So you notice it's just oscillating up and down, up and down. So this is not approaching a single number at all. So this is called a diverging function. And it's because it is oscillating between negative 1 and positive 1. Okay, so the next one down below, we're going 1 to 1/2 to 1/3 to 1/4. The next would be 1/5 because this is 1 over n. 1/6, 1 over 100, 1 over 1,000, 1 over 1,000,000. We are approaching a number. We're getting closer and closer and closer to a number. 1 over 1,000,000, 1 over 1,000,000,000 is approaching 0. So this converges to 0. So there's two different ways we can write this. If we're writing it in end behavior notation, as x is getting bigger and bigger, approaches infinity, f of x is going to approach 0. If you want to write it in limit notation, the limit as x approaches infinity of the function 1 over n is equal to 0. You are totally fine in this course writing this in end behavior notation, and you're not doing both ends end behavior. It really is your right end behavior if it converges. Next one goes from 2 to 1 1/2 to 1 1/3 to 1 1/4. So you notice the top is going to go up by 1, the bottom goes up by 1. So this is going to converge and get closer and closer to 1. So as x approaches infinity, f of x, so as the term number approaches infinity, that's what that's saying, f of x is approaching 1. 2, 4, 6, 8, 10. We are adding 2. It is always going to keep going up, going up, going up, going up, going up. going from 10 to 12 to 14 to 16 to all even numbers, and it doesn't stop. It just continues to increase. So it's not approaching a single number. So this diverges essentially because it's approaching infinity, but we don't really write it in, when it's diverging, you're not writing it in limit notation or in behavior notation. Now, the last set of problems you're going to look at are problems that are equations, and they're asking you to look at these equations and figure out whether it is converging or diverging. And to do that, we have to put some rules down. So on the right side of your paper, we are going to be looking at reviewing something we did back in September, which was the horizontal asymptote rules. Horizontal asymptote rules. Because they're going to tell us what's going on here. There are three cases here. If it is top-heavy, which means the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Second scenario is if it is bottom-heavy. If you have a bottom-heavy function where the degree of the numerator is less than the degree of denominator, like x over x squared over x to the third. So the bottom is bigger than the top of the highest degree. If it's bottom heavy, the horizontal asymptote is y equals 0. It should be familiar to you. If they have the same degree, like you have 2x over 3x, like 2x over 3x, we take the coefficients. It's y equals 2/3. So these are the leading coefficients. So how this applies to these functions is if it is bottom heavy or it has the same, this is going to converge to whatever that number is, whether it's 0 or whatever the coefficients are. This is a case when it's top heavy where this diverges, because it does not approach a horizontal, does not approach a horizontal asymptote. So it's going to just kind of probably continue to go on towards infinity. So let's look at this first example here. 3n over n plus 1. So this is an n to the first over the n to the first. These degrees are the same. Since these are the same degree, then this has a horizontal asymptote that would be y equals 3 over 1, because the leading coefficient is 3. This leading coefficient is 1 that's not showing up here. So 3 over 1 is 3. So therefore, this is going to converge and approach 3. So as x is approaching infinity, so as the term number is getting bigger and bigger, f of x is going to approach 3. If you wanted to test that, again, you could just stick numbers in there. Put 1 in for the first term, simplify. 2 in for the second term, simplify. 3 in for the third term, simplify. 4, and you keep going, and you'll see that this is going to converge and approach 3. Example number 2 is 5n squared over n cubed plus 1. So notice that this degree is 2, this degree is 3. This is called bottom heavy, because there's more degrees in the bottom than the top. If you recall, according to our rules, if this is bottom heavy, the horizontal asymptote is y equals 0. So this is going to converge, and in limit notation, as x approaches infinity, f of x is going to approach 0. So again, if you wanted to test this out, you'd put 1 in for the first term, simplify, 2 in for the second term, simplify, 3 in for the third term, simplify, and keep on going. And you will see that they're getting closer and closer and closer to 0, as we noticed from the patterns from above. Finally, the last problem here, we have n to the third power over n to the second power. This is a 3 over 2. So this is top heavy. When we have a top heavy function, there is no horizontal asymptote. When we have no horizontal asymptote, this function is going to diverge. And then you don't, when it diverges, you don't provide the limit or the interval over the end behavior on the right side. So what you're going to do for the remainder of this period is flip to page number 5 in your packet and complete questions 1 through 10. And you are going to look at this problem. This is the first term, the second term, the third term. They want you to find the next 4 terms following that pattern and graph it by term number and what the y value is. So same for these 4. Here, these problems here, these are a list, like the top part of the page before, and they want you to know whether to provide whether it's converging or diverging. If it converges, provide the limit. And 7 through 10 are like the problems we just completed, where you're checking to see the horizontal asymptote and that relationship. So that is your work for today. So that is it.